Hello, thank you for coming to my talk. My name is Petr Chalupa, and I work on TruffleRuby, which in Oracle Labs, which is a research organization within Oracle. So first, before I start, I would like to make sure that you understand that this is a research project, so don't do any investment based on whatever you hear today. But first, I introduce some of the technologies we are building this on. Then I explain how we actually execute the Cextensions, and then I move on to talking about what our old approach was and what problems we had. And then I'll talk a little bit about our new approach and how it improved our support for Cextensions. So the technologies. So TruffleRuby is an alternative Ruby implementation. We aim to be a drop-in replacement for CRuby. So we support Cextensions. We have a good startup time, which is important for development. We also have just-in-time compilation, which means that we are generally faster than any other implementation. And if not, please file a bug, because it's usually just some issue or some case we didn't optimize yet. So we got the name from Truffle, which is a language implementation framework. And it's basically a specializing, which means self-modifying abstract syntax tree interpreter. Which means that implementing languages with abstract C interpreter is actually quite simple. It's the simplest approach. So you can implement a language quite quickly with this. Part of the Truffle, there is a Polyglot protocol, which allows the languages, all the languages implemented in Truffle, to talk to each other, to exchange values without transforming them in any way. So it means that there is no usual barrier between the languages. There's also an instrumentation API, which with a little bit of work, if you instrument your nodes, then you get a multi-language debugger and other tooling like profilers. So this is the slide we usually show to explain Truffle. So it basically works when you parse your language, you turn that into nodes. And at the beginning, the nodes in Truffle are initialized, which means they didn't see any code, they didn't execute yet. So for example, if you have a node which represents some addition, so as it sees first values, for example, integers, it replaces itself with a different node which knows how to add two integers very efficiently. And this is happening in all the nodes. And when this tree of nodes is stabilized, then it can be partially evaluated and compiled together. And during the partial evaluation, all the code which is responsible for the node replacements just drops out, and what you are left with is the very well optimized machine code. To be able to do that, you need a compiler. We use Graal Compiler, which is a dynamic compiler written in Java, which means it's basically a Java library, so Truffle can directly talk to it. So in combination with Truffle, you get all the important optimizations like inlining, splitting, which is also sometimes called method cloning, and partial evaluation. And this means that all these optimizations are done, let's say, below the level of the implementations of the languages, which means that you get it for all of them, and you need to implement only once, and you can also optimize them together. And of course, the last piece is that at the bottom there is a Java VM, which executes the compiled methods provided by Graal. And of course, there is a garbage collector there, and it executes runner Java. We distribute all of this in a Graal VM, which is basically one distribution of the Java VM and the libraries which contain the Graal compiler and the Truffle framework, and also some of the languages you can run on this. So the Java language is Java, Kotlin, Scala, or the dynamic languages Ruby, JavaScript, R, Python, and also, as I show on the next slide, C, C++, and Fortran. So one of the other languages there is Sulong, or LLVM bitcode runtime. It is also a technical interpreter with the just-in-time compilation, but very fast. And that allows you to execute any code, any language which you can transform to LLVM bitcode, so C, C++, and Fortran. And especially the C is quite important for us because TruffleRuby needs to run C extensions, so our C extensions are executed with so long. Of course, those both languages are implemented in Truffle, so it can be optimized together with Graal. So there are no language barriers here. We also have a little bit different VM, subset VM, which its tooling allows you to compile ahead of time Java applications. So for us, that means because Truffle, Graal, and the TruffleRuby implementation and the Sulong, which is the LVM interpreter, are all written in Java. So we can take all of this and compile this into one executable, which can then evaluate Ruby. And this gives us no slow startup limitations. So we have a short, quick look at some of the numbers. So if you use the TruffleRuby native image, which is created and running with the substrate VM for the hello world, it takes just 25 milliseconds, which is even faster than CRuby. So how do we run C code and C extensions? So basically the key thing we use is that the Truffle allows gives us interoperability between the languages. So that means that when we are looking at some C extension which is running in our runtime, then when we are looking at the variables which has the type value, they are Ruby actual Ruby objects. They are not C objects. And the Polyglot protocol allows us to talk to the foreign objects like that. Another concept we need to understand is that is difference between managed and unmanaged memory. So the Ruby objects are implemented as regular Java objects, and they are managed, which means that they are managed by the VM. They can be garbage collected, they can be moved, and stuff like that. And then there is unmanaged memory or native memory, which is allocated by the LLVM for structs, stack, or native arrays, and stuff like that. So we cannot just take a managed object, a Ruby object, and put it into unmanaged native memory. So we need to do some tricks how to get around this, and this is the main topic basically of this talk. And of course, optimize this together. So what is the Polyglot protocol? So this is another API which is part of the Truffle framework, which allows you to define functions on objects, which then it makes it easy to communicate with foreign objects in your language. So for example, if you're looking at a C code where you have a Ruby object, and then syntactically it means read a member from a struct, that's translated to calling a has member on the Ruby object, and if it actually has members, then you can read the member from that Ruby object, even though it is actually C code. So this is one set of the messages we have, and then there is isPointer and sPointer, which is important in a point where you want to store a Ruby object, which is a managed memory, to some unmanaged memory. So if you want to store a Ruby object to a member of a struct, you cannot just take it and somehow keep it there. You need to turn it into a pointer. So for that, the Ruby object has to support the conversion to a pointer, and you can ask if it does or not with the isPointer method, and if it does, the LLVM interpreter will convert it and store the pointer into the native struct. And this is again implemented with the specializing nodes, as almost everything is in Truffle, which means that this works somewhat like follows. If you have if a C code reads something from a foreign Ruby object, at the beginning it's initialized, and first time it's executed, it asks the Ruby language how the read from a Ruby object actually looks like, and that initialized node representing the reading from the foreign object is represented with the different nodes which knows how to read the value from the Ruby object. And then later this is compiled efficiently. So when we are looking in a C code and in TruffleRuby, what does it mean? So this is an example method taken from the zip standard library. So in the condition we have nilp predicate, which in our implementation calls back to Ruby and calls the regular nil question mark method. So this actually means that we need to take a Ruby object stored in the input member of zstream, which is an inner struct in gzip file. On the next line, we have the rstring len macro, which again needs to extract a Ruby object from the inner struct zstream. Then it calls regular Ruby method length on it, and then it has to be converted to C-long. So it could be returned here. At the bottom, there is a call. So again, we need to read the receiver from the gzip struct, and then we pass it some arguments. So it's a little bit more complicated. So our old approach to this was, so I've mentioned before that there is a problem that you cannot just shove managed object in an unmanaged memory. So one of the tricks we did in the past was to create handles for managed objects and store them instead, which is basically just a number. If we do that, we needed to have some table which maps the numbers we've used, the handles, to the managed objects, which meant that we had strong references from the table to all the objects which we were converting to the handles. So then we needed to also manually release the handle and delete the reference from the handle table. So that meant that if we had a method like this in the zlib standard library, we had to insert conversion functions which were converting between the managed objects and the handles. So in the first line in the condition, we had to convert from the handle, which is the only thing which could be stored in the member of the native struct, back to the managed memory using the handle table. On the next line, we had to do the same. And the third line, we had to convert in the opposite direction. So we had to get the handle for the nil object to be stored in the input member of the z struct. And below that, there is some representation of how it looks like in the memory. So the rectangles are for just the numbers. The red links are representing strong references. And circles are for the rest. Of course, you can imagine you need to store stuff in the zstream struct in the zlib standard library quite often. So this resulted in the past we had about 200 handle methods added to the standard library, which was not very good because we had to maintain these changes of the standard library. So we wanted to get rid of that. So the first step we did to trying to rid of it is by trying to turn more things from unmanaged stuff to managed stuff. So we created some Ruby object, a managed Ruby object, which was behaving as a C struct. And where we would be defining a zstream struct, we would replace it with the managed one. So then we wouldn't need to convert from the handles to the managed objects and back that often. But unfortunately, that was useful as you reduced the number of patches, but it still needed some changes, like you need, if it's a managed object, you need to call initializer. Sometimes you had to change stuff into pointers where you would otherwise have it stored on a native stack. And if you had inner structs, then you would also need to do some special handling for that. But it was a step in good direction. So, for example, this is the piece of code you've already seen. So that could be replaced, or all the handle methods could be removed because the zstream in this code was actually a managed object. So when there is a zstream arrow input, this would translate to reading a member from a foreign object. This is not a reading from a native memory. But at the end, you can see that there were other changes needed, calling the constructor, changing it to the pointer and stuff like that. So this was a step in a good direction, but it was not good enough. The next problem we had is leaking handles. As I said, the objects were kept with a strong reference from the handle table as long as, unless you didn't manually free them, which meant for us that we had to go over the Cextensions, make understand them, and release the handles in the right places, which is not really feasible, because if you have something really complicated, like for example some data structure from Nokogiri, there is lots of links between each other. It's not easy to figure out where are the right places to release the objects, so we were leaking handles and therefore the managed objects. So this was another big problem we had. So how did we solve it? So first, we are now wrapping all the Ruby objects in a wrapper, which always know how any of the Ruby objects can be converted, lazily converted to a pointer. And because we have this wrapper, we can also track whenever the object needed to be converted. So whenever you are looking at values in C code, it's always the wrapper now, not directly the Ruby objects. And to do that, whenever we call, whenever we call from C to Ruby, we need to first unwrap the arguments, including the receiver, so we get the actual Ruby objects, and we have to wrap the return value back again. And what this allows us to do is run the code unchanged. So this is again the pass-through input method from zlib. As you can see, there is no modification. And if I try to interpret it for you, so for example, if you have the Z arrow input, which now means that in the input there is the pointer previously converted from the managed object which we try to store there. So this is then unwrapped back to the object when you are trying to call the nil question mark method implemented in Ruby, because this is how the nil predicate is implemented for us. On the second line, the input member of the struct contains just the pointer, the number, so that's just passed into the C function. And the third line, you have qnil constant, which because we are in C, this is actually the wrapped value wrapping the nil Ruby object. So we get the pointer for the nil here and store that into the native struct, into the input member. So this means that we don't have any more changes, or we don't need to maintain any patches. Another problem was the memory management. So we stood back and had a closer look at how actually MRI manages memory. And MRI manages memory in two ways, or it keeps objects alive in two ways. So first one by stack marking, so anything which is on any value which is on stack in Ruby will not be garbage collected. And the second way is whenever you have some C data stored within a Ruby object, where the native C data store some other Ruby objects, you can also assign with that marking function, which will keep the data, the Ruby objects stored in the data alive for you. So we did for both of these, we did something similar. So first, how did we deal with keeping the objects alive when they are on the stack? So basically, whenever we enter a C call, we create a list where we put any lazily converted Ruby object when it converted to a handle to this list, and we keep strong references from this list to all of these objects. And whenever we leave a call from Cextension, we just discard this list, freeing all the objects which were needed to be converted. So we will no longer keep them alive. So how does it look like? So we have a stack, and we are about to call a C method. And when we do, we create a preservation list Just a reminder, the red links are for strong references. And whenever we store or assign some Ruby object into a native memory, in the code like this, we take input, which is a Ruby object, and we are storing it into a native member input in the Z stream. Then we need to lazily create a handle for the input object. We put that into the handle table, and we did a change that now the handle table only references the managed objects weekly, so they can be, the handle table no longer prevents garbage collection, but we put this object into the preservation list. So if there is another assignment, again it's converted and it's added to the preservation list. Then let's say there is a call to Ruby, so there's nothing happening here interesting. When it unwinds, it still remains referenced as it should be. When we unwind the C call, then the references to the handles disappear, and also the reference to the preservation list disappeared. So we can now garbage collect the A and B objects which were stored in the data structure in C. So this was the first part, and the second part is how to deal with the mark functions. So in MRI, you can assign some C data with an object using the type data make struct, and for that you also need to assign it some marking function which makes sure that the objects are not garbage collected, because they can be stored only in this C data structure, and the garbage collector needs a way how to find these objects. So this is what this is for. So we are using the same code, but our implementation of RubyGC mark and stuff around it is quite different. So what we do is that we keep weak list of all the marking functions, and we have a fixed size buffer for all the wrappers or the managed object which needed the conversion to a pointer. And whenever object is converted, it's put to the list I've already shown you for the stack, and into this fixed size list. And when this fixed size list is full, we run all the marking functions, and at that point we create strong references from the objects which are holding the another objects through their C data through the marked function. And then we can clear out the fixed size buffer, because we no longer need the references from there, because they are moved to the list of marked objects from the initial Ruby object. I hope that will be clear with a picture. So this is the situation at the beginning. We have some Ruby object, which has the inner struct, which can store some another Ruby objects. And you have a list for objects which are marked, but the marking function for this struct of the object A. So on the first assignment of a value, let's say if you assign B to the member of the struct, then that's lazily converted. Also, sorry, there is the lazily created handle for that. That's stored in the handle table. There is the weak link created there, so you can look up what's actually stored in the struct. And the important part is that we put the strong reference to the preservation table, which is the fixed size buffer. And later, when the preservation table is full, we run all the marking functions. So at that point, we figure out that B is stored in some of the C data of A. So we can put a strong reference from the A object through its list of marked objects, and we can clear out the preservation table. If you assign some new value to the C data of A, then it will also create a new handle for it. The C object will be strongly referenced from preservation table, and for some time the list of marked objects of A will keep referencing the old objects. But when the preservation table fills, it fixes the link, and B now is no longer strongly referenced from anywhere. So it can be safely garbage collected, and later when there is no reference to A, can be also garbage collected. So we no longer have any problems with leaky memory. So in conclusion, what does this mean? So we had much better compatibility with Cextensions. So in practice, we can run without patches out of the box. Standard libraries we have, so that's OpenSSL, zlib, psych, which is the YAML implementation, etc., and syslog. From the database drivers, we can run SQL, SQLite, MySQL, and PG, also without patches. And this is particularly important because you don't need to replace that with some Java implementation or anything like that for JRuby. It just works. And we know that we run Puma, Neo4r, Buyback, WebSocket driver, Rack, MS Message Pack, Nokogiri, and probably much more CAMs. And would like to know from you what experiments were successful for you. So if we have a look at the end in the table, the small comparison, we start with the Cextensions on CRuby. Cextensions are of course supported, and JRuby they are not supported, so you need some replacements, which leads to problems because you then have, for example, different gems on development if you want fast startup, and different gems on production. But on TruffleRuby, the Cextensions are supported, so you don't get these issues. On CRuby, you sometimes need extensions because for performance reasons, Ruby might not be fast enough for you. In JRuby, the situation is similar, but you need to keep two implementations around, one in Java and second one in C if you need that for MRI. But on TruffleRuby, in general, you don't need extensions. TruffleRuby generally should be fast enough, so you shouldn't be forced to write C code or Java on anything in any other language than Ruby. So we have one example of that, for example, the pure JSON implementation works faster on TruffleRuby than if you run it on with Cextension on CRuby. Of course, all the implementations support FFI, but the problem with that is that not every gem is written with FFI, so then it doesn't run if it's not written with that. So the general status of TruffleRuby is that we are very much ready for experiments. I would like to encourage you to try that. I guess the best thing to try are smaller services with less dependencies where you would profit with increased performance. So you could try running that. Let us know if something breaks. We are actively monitoring all the issues and we are fixing them. So if you file a few issues, we fix them and you get the benefits of better performance. And installing Ruby TruffleRuby is really easy nowadays. You just run install TruffleRuby with any of the Ruby managers, and that's it. Before I end, just a reminder, this is a research project, and that's everything from me. Thank you for your attention. I will be happy to answer any of your questions.
Hey, that's everything you did that you showed today is just incredible. Like, blew my mind. The way that you've been dealing with the Cextensions, I've never seen that done before, ever. And yeah, it's incredible. So this is sort of tangentially related. How is the integration with Project Loom going? And when do you think that will be ready for trying out or experimenting with?
I'm not sure about when it will be ready. I know we are working on it and we have some prototypes testing it, how it works out for us. So we are working on it, and when it will be ready, we will shortly follow with some better support for fibers. But sorry, I don't know when that will happen. Sorry.
That's no problem. Thank you.
Thank you. Any more questions?
So I was reading that biggest stumbling block from moving like an application from MRI to TruffleRuby was kind of Nokogiri and Cextensions. Do you think that TruffleRuby is ready to just kind of be a shoe-in replacement for MRI, or are there still some
the issues we have, the Ruby itself is quite complicated. So we didn't catch all the corner cases or implemented we still know that we are missing few pieces here and there, but it should be the small pieces. So when you try some small things to run, it's probable that it will work out of the box. The larger it is, it's more probable that you run into some bug with missed or some corner case we didn't implement it yet. So I wouldn't recommend in general for production, but for any experimentation and for trying small things and see how it works, we are perfectly in that state.
Cool. Thanks.
And especially the Cextensions shouldn't be a problem now, basically. So you can try to install and compile any Cextension with TruffleRuby, and yeah.
You mentioned Fortran. Is it LLVM Fortran?
I'm not sure, sorry. Because the Sulong is interpreting on an LLVM bit code, so it has to run the front end, the front end which translates Fortran to LLVM bit code. So if that is your question, then yes.
Okay, because it's just they decided just to include it in LLVM, so it's a pretty experimental feature. I mean, GCC has Fortran for many years, and it's used for spec CPU benchmarking, but LLVM, it's a very experimental feature, although the committee decided to make it a part of LLVM.
Yeah, I'm sorry, I don't know much details about this part because we don't have any Fortran extensions or anything like that. Okay. So I know they did some experiments and there is some support, but I'm not sure how limited it is. Sorry.
Thank you.
Thank you for your question. Okay, thank you very much for your attention.